some of the excuse me, some of the voltages measured like they would only switch between like two different values that were like right next to each other. And so for those, would you just use the uncertainty that's inside of the manual?
So can you give me an idea of how the values switched? I mean, what the values were?
Yeah. So for example, for part two, I use the smaller multimeter to measure voltage values. And like for example, for one of the resistors, I would get values of 2.75 volts or 2.76 volts, and they would switch like regularly.
Just between those two values?
Yeah.
So I would just say 0.01 volt is the uncertainty, right? I mean, that's how I would look at it.
Okay, what about for values that were like steady? Because I got some of those as well.
Oh, it didn't change? Okay,
Yeah.
yeah, then, yeah, and I did have one student go by what the manual said, and I think it was 0.4%. Maybe that was on the resistance. You can go
Yeah.
by what the manual says, since you have the
Okay.
manual.
Should we go by what the manual is if the manual's uncertainty is greater than the uncertainty that we're measuring?
That's a good point. Yes.
Okay.
I was assuming that as you were doing the measurement, the uncertainty that you would observe was higher than what the manual would provide. But
Well, so like for a lot of the previous labs, I had like a lot of variation, but for this lab, I've had like all my measurements have had like little to no variation.
okay, well that's good though.
Yeah.
Then yeah, then go by the what the manual says, and that's going to take into account probably systematic errors. Well, no, not all systematic errors, because we're not taking into account the meter in the circuit, the ammeter in the circuit. So yeah, go with the manual then.
Okay.
That's a great question.
Got it. Thank you.
Other questions? So, anybody missing a resistor? Oh, let's see. So you got a 2% difference between the currents. So so in one case though, Morgan, yeah, I would go with the bigger uncertainty, but here's the thing, Morgan. When you measured I sub s, the meter was in the circuit. So then the I sub s that you measure with the meter is probably going to be smaller than the I sub s you calculated. Is that what you got? Yeah, because the meter has because the meter itself has resistance. Yeah, when I collected the data, I saw that small error, around 2%, maybe as much as 3%. Again, that's going to depend on how much current you have in your circuit. So you can always attribute that to the fact that your ammeter, so you have a systematic error. It's the ammeter, right? You did it once with the ammeter in and then you took it out. But if you want to take into account if you want to use the uncertainties based on the manual, then go ahead, you can do that. Yeah, I think I got very similar to what you got, if I remember correctly. I think around 29 milliamps, and my calculated one was like 29.6 or 29.7. That's about right. And then In fact, if you did the experiment again and you change this setting on the, you can't do it on that meter. These meters, that scale is weird, 20. But I bet you if you change the resistance value, the meter reading, the 20 milliamp scale, you probably get 20 milliamps because the resistance of the meter is significantly more on a 20 milliamp scale. Though I wouldn't try it because you're at the limit of the scale. Yeah, and yeah, that's because of the meter in the circuit. That's part of it, to show you part of this lab is to show you the effect of the meter in the circuit. It's actually better to actually have you see that. Because a lot of times people will be unaware of the fact that the meter affects the circuit too. But Morgan, if you want to use the uncertainties based on the manual, that's fine. Other questions? So I guess you might, under the tables, under table 1 or table 2 or table 3, let me know how you determine the uncertainties. Just a sentence saying you used the manual or you just did it by, it's an estimate. I think for everyone in the class, I think it's good to let the reader know how those uncertainties were determined. Other questions? So is anybody missing any equipment for this lab? I hope you have collected the data already. Don't wait till the end because this will take you forever to write the lab report. I'm not kidding. I had some people missing the 560 ohm resistor. So if you have something missing, you got to contact Tyler. If you need a fuse, you got to contact Tyler. Tyler has office hours tomorrow on Zoom, and so you can talk to him regarding if you have anything missing, or you can just email him today and set up an appointment to pick up anything that you need to pick up. But the 560 ohm resistor and the 150 ohm resistor are blue. And it's really, for me, based on with my eyes, it's hard to see the color code on the 560 ohm resistor. One student didn't get the 560 ohm, but he said he had a 220 and a 230. I'm sorry, 220 ohm and a 330 ohm resistor. He put them in series. I thought that was a great idea. And so those two replaced the 560. And if you wanted to buy a resistor, they are very cheap. I think Fry's might still be selling those. But anyway, I do want to use some of this time to answer your questions because this is due next week. And to me, this is an important lab because you do a lot of analysis and building circuits in this lab. No more questions. I'm hoping that you've all collected the data. Make sure that you show a picture of your setup, okay, including the multimeter. I do want to point something out. In the lab, I say to measure the power supply voltage, but I didn't leave a spot for it in the table. So what you want to do is below the tables, what you want to do is list the power supply voltage. Okay, so this version that I'm showing you on the screen is not the same as the version you have, because I added this the other day because somebody brought up a question regarding the power supply voltage. It tells you to measure it and record it, but there's no place to record it. So you'll put the power supply voltage below table 1 and table 2 and table 3. Okay, so I added all this. Let me know if there's anything unclear or okay. All right, so since you folks are quiet, I guess you don't have any more questions. I'm going to continue with the discussion on chapter 29. I want to finish up chapter 29. So we finished off the class talking about the torque on a loop of wire in a magnetic field, a uniform magnetic field. And we came up with an expression that the torque is the magnetic moment crossed with the magnetic field. And the magnetic moment is the number of turns in the coil times the current times the cross-sectional area of the loop. And we define the area vector as the magnitude of the area times the normal to the loop. So let me play this little demo. This is from MIT. MIT has a bunch of little demos like this, showing you the torque on a loop of wire in a magnetic field. Along the axis, you see the direction of the torque vector. So, sorry, it's a little choppy. Here's an application of the torque on a loop of wire in a uniform field. So this is an ammeter. This is one of the old-fashioned ammeters. So here you have a loop of wire, and the current that goes through the loop of wire is due to somebody measuring the current in the circuit. So when a student connects this ammeter to a circuit, there will be a current going through this loop in this magnetic field, causing this thing to rotate. But it's not going to rotate continuously because at the top there's a spring. The more this thing rotates, the bigger is the torque due to the spring. So the amount by which this loop rotates is going to be indicative of the current in the circuit. And so you can calibrate this thing based on the current to measure its value. Another important application of this idea of a torque on a loop of wire in a magnetic field is the motor. The motor is a device that converts electrical energy into mechanical energy. And it's really a generator, but working in the opposite direction. And I'm going to demonstrate that to you over the next couple of weeks because I have a demonstration DC motor that can also act as a generator, and I'll use that same device as a generator in about a week or two. Really, if you're trying to understand how a DC motor works, you just think of it as a loop of wire in a magnetic field. There's really a couple important parts to the DC motor. There's the armature, which is a coil of wire that's mounted on a cylinder. And the armature is the part of the motor that does the mechanical work. It transfers energy from the motor to the surroundings, mechanical energy. So the armature is one key part of the motor. And then the other is the commutator and the brushes. The brushes are basically stationary contacts that rub against the commutator. The brushes transmit the energy from the power supply to the commutator and the armature. And the commutator has to be designed so that when the motor, the loop of wire rotates by 180 degrees, the direction of the current in the loop is reversed. Otherwise, if you don't reverse the current, what happens is the torque reverses directions and you get a motor that just oscillates back and forth, which is completely useless. So here's a figure of what happens before and after when the loop is at 0 degrees and then the loop is rotated by 180 degrees. The force vectors go in the opposite direction, which means the torque goes in the opposite direction, and that means that the motor is going to want to rotate in the opposite direction. So let me show you a motor that I have here. And I'm going to have to change the view. And magnify it quite a bit. Okay, let me adjust my camera some more. All right. Can you all see this motor? This is the DC motor. Can you all see that okay? Okay. And then behind it is the power supply. So let me just show you the various parts of the motor. Let me turn this around. Oops, I gotta connect it. I disconnected the motor. Well, I'll connect it later. So the main parts, this thing that rotates, there's a coil of wire. If you can see this coil of wire, this is the armature. This whole thing rotates. This is what's going to deliver the mechanical energy to the surroundings. So basically you have a loop of N turns here. Okay. Then there's more wire below here. And this wire that's below, I'll lift this up. This wire that's down here is used to create an electromagnet. This wire is wrapped around some iron. And so when you run a current through this loop of wire, you produce a magnetic field. The magnetic field magnetizes the wire and produces a bigger magnetic field. Unfortunately, we're not going to talk about magnetic properties of material this semester. Just don't have time. Then you have the brushes. These are for the electrical connections. Hold on a second. Okay. These are for the electrical connections to the commutator. Our commutator, there's two sets here because I can run this as an AC motor, but the commutator is right here. And I don't know if you can see it, but the commutator is split here, right over there. Okay? The commutator is split right here. If you can see that, I don't know. And this is where the current, once the contacts get to this point, this is where the current reverses direction. So let me put my brushes back in. So as this rotates, when the motor is in this orientation, the normal to the loop is up, the magnetic field's this way or that way. But the angle between the normal to the loop and the magnetic field is about 90 degrees. This is when you have maximum torque. When the loop is like this, where the normal to the loop points in the direction of the magnetic field, here the torque is 0. And this is where you reverse the direction of the current. You want to reverse the direction of the current when the torque is 0. not when the torque is maximized. Otherwise your motor ain't gonna work. Okay. So let me connect my motor. I gotta do this right before, otherwise I'll screw it up. And let me turn on my power supply. I'll give it a kick. And there it goes. I can set it to a voltage where it starts by itself, but then I'll blow a fuse. This is running at 5 volts. I'm only putting in 5 volts on this thing and it's running. I could go to 4 volts once it started. So this thing is running at 4 volts. So you folks are going to build a motor starting next week. You folks have in your lab kit a DC motor kit. It comes in a bag like this. You have a coil of wire, the board, a bunch of nails, and you have instructions on how to build it. You have to build it well because you're going to be graded on what voltage it runs at. We provided 2 D-cell batteries, so we want you to get it to run on 3 volts or less. You can actually, if you build it right, you can get it to run on 1.5 volts. So when you're done, you'll have something. It looks like this. This is a motor that a student built. This is the armature. Okay, that's the armature. And then the commutator, it's split. And then this is the electromagnet, this part with the magnet wire wrapped around it. Most of the parts are cheap except for the magnet wire. And you got to be careful with the magnet wire. Don't screw it up because replacing the magnet wire is not easy. We might have extras, but I had a student last year try to buy it from Amazon. Of course, you got to buy the whole roll, which is not going to be of much use for you probably unless you're going to design magnets. Just be careful with this magnet wire. So here's one from another student. They actually use bearings. This is one of those projects where you can do whatever, a lot of things. You can have fun with this, okay? So I'm covering the person's name on here because they read their name on here. And this one actually ran on 5 volts. So this wasn't very efficient, okay? But it's ran on 5 volts. And I'll have these here for next week. Okay, so you'll be building one like on that. Again, you're going to be graded based on the voltage. Normally, when we do this in class, I expect you to do it 2 volts or less. But when we do it in class, you can come to campus and use our power supplies to test it out and make it work better. Most students don't have power supplies, so what I've done is made the cutoff for an A little bit higher, so 3 volts instead of 2 volts. And we've had students run the motor at voltages less than 1 volt. Now, the one important thing I did here that I don't want you to do is, when I hooked this up, I hooked the magnet and the coil in parallel. You're not going to do that in the lab, because you might be running too much current and maybe melt a coating on the wires. You're going to have to wire everything in series. If you don't run things in series, your batteries will go down real quick. You'll actually be running so much current in your motor that you might melt the coating. That wire is coated. You melt the coating, then you mess up your motor. So you're going to have to hook up everything in series when you do that. Okay? Questions on this? Somebody asked me the other day, what's the handle for? Why do you think? Why does this have a handle? Anybody want to guess as to why this thing has a handle on it? Yeah, to generate electricity. So I'm going to use this in a week or two to show you how to generate electricity. I would disconnect this. I would put a voltmeter here. Hopefully I can get a big voltmeter so I can display the voltage. And then this will be hooked up to the power supplies because I need a magnet. And then I'm just going to hand crank it and I can generate a voltage. Okay, that's what I will do with this guy. This also runs as an AC motor, but although I was having trouble getting it to work, where the commutator is not split, and I don't need to split it because an AC voltage changes direction. So I don't have to have this splitting here because of the fact that the AC changes direction. So I just have these two connections for the brushes. So this is a split ring commutator, or slip ring, sorry. Okay. No questions? Okay, let me change the magnification on here. So there's one more topic I want to talk about. It's the Hall effect. So imagine we have a flat conductor in the magnetic field, like you see in the picture. The gray thing in the picture. Its height is d, its thickness is d. And I mentioned those dimensions because they're going to be relevant in our discussion. And it's carrying a current I to the right. So the current is to the right. Which means if you have positive charge carriers, they're moving to the right. If you have negative charge carriers, that means they move to the left. Current is still to the right. We have a magnetic field that's directed into the plane of the screen. So that's going to cause a force on the charge carriers. If you use the right-hand rule, I cross B, you'll find that there's a force that's upward. And that upward force is going to be, that force is going to be upward whether you're dealing with positive charge carriers or negative charge carriers. Okay. That upward force is going to be is going to affect either the negative charge carriers or the positive charge carriers. Either one, the force is going to be upward. Remember, the negative charge carriers are moving to the left even though the current's positive, in the positive direction. So let's say we have electrons in motion. This is a wire and we have electrons in motion in this gray conductor. The force on them is going to be upward. So you're going to have a bunch of electrons moving toward the top of the conductor, leaving a deficiency of electrons on the bottom part of the conductor, which means that the bottom part of the conductor is going to be positive, the top part of the conductor is going to be negative. that means you're going to have an electric field that points upward because electric fields go from positive to negative. So you have an electric field that points upward. So that means you have a potential difference between the two ends, the top end and the bottom end of that conductor. That's the Hall effect. The voltage that you measure between the top of the conductor and the bottom of the conductor is called the Hall voltage. And the electric field that's established because of the fact that these charges are moving in this magnetic field is called the Hall field. If the charge carriers were positive in this material, then the positive charges would be moving up, the negative charge would be moving down. In other words, the positive charges would be moving up, leaving a deficiency of positive charge on the bottom. So you'd have more positive charge on the top and more negative charge on the bottom. Then the electric field will point straight down. And so the potential difference, or the potential, will be decreasing downward. Because of this effect on the electric field, then you can use the Hall effect to determine whether it's electrons or positive charges that are moving in a wire, in a circuit. And it was the Hall effect that allowed us to determine that it's electrons that are moving in a wire, in a circuit. Now, typically what we do is we put this material in a uniform magnetic field. So if you put it in a uniform magnetic field, you'll establish a uniform electric field. See, what happens is, let me go back. Charge will separate until the force due to the electric field equals the force due to the magnetic field, until you reach an equilibrium. And if that field's uniform, if the magnetic field's uniform, the electric field will be uniform. And so we use the Lorentz force, QVB equals QE. And you can show that the established field is the drift velocity of the electrons times the magnetic field. And again, if the magnetic field is uniform, the electric field is uniform. The electric field then is the potential difference between the top and the bottom of that conductor divided by the distance between the top and bottom of the conductor. So delta V over D is just the drift velocity times B. You can measure the Hall voltage with a very sensitive meter, not with a typical multimeter. You can measure B, okay, and then you can measure with a ruler the distance from the top and the bottom of the material. So realistically, if you can measure this guy, B and D, you can actually determine the drift velocity. So this is a way one can actually measure the drift velocity of the charges in a wire. In fact, since I is the number of charge carriers per unit volume times the drift velocity times Q times the area of the area through which the current is moving, which in this case would be the dimensions D and T, then we can use this and our knowledge of the Hall voltage to actually measure the number of charge carriers per unit volume. We can actually do that experiment. We can do it for semiconductors, conductors, whatever. So by making these measurements, we can actually test our knowledge of these theories. You know, what is current due to? How do we explain resistance? In the wire, what's moving? Electrons or positive charges? Those are questions that can be answered using the Hall effect. And then there's also something called the quantum Hall effect, for which the Nobel Prize was won later on. You can also use the Hall effect to measure magnetic field. There's these devices called Hall probes, which are used to accurately measure magnetic fields. Typically, one doesn't spend a lot of time on this topic, but it has a lot of interesting applications. Any questions? No questions? So I did change, in your notes, I did change the slide. I added a little bit more information on the slide. So I'm showing this in the video, so you can use this slide in the video to answer the last homework question. The last homework question is basically based on this slide. Basically to get you to understand what the basics of the Hall effect is. Okay. Oops, I see one new question. Just 1 second. Which slide do you want me to go to? Hold on a second. Is it this one? Because I went ahead. Okay. Did you have a question on this slide? Oh, just copying formulas. Okay. I hope you have the notes. That's fine. But I hope you have the notes for this. Are we okay? Okay. Any other questions? I kind of want to put it back to the previous slide just because this is going to help you with your homework. Yeah, this will help you answer the last homework question. Questions or concerns regarding the lab, or like I said, next week I'm going to talk about the DC motor lab, and I kind of said a lot about it already. I might just say some rules, etc. But it's the next homework is due Friday the 23rd. I'm going to try to have them due on the homework's due on consecutive Fridays, so that you have that's why I moved the exam date, so that you'll have enough time. Because I didn't want to rush. Because in your case, I would have to really rush the last homework assignment in a unit. With the Friday group, I only give them one less day to do one of the homework assignments, so they're okay. But for you guys, you'd have to do it in like 3 days or something. So I didn't want to do that. Other questions? Let me know if there's, with this lab, again, all these labs are kind of new because they're online. If you have any suggestions to the labs, let me know. Okay. Just send me an email. Because it's way different doing the labs online than it is in person, because if there's something missing in the lab, when we're in person, I can just see you in my office typically. So things are a little bit different online. Okay, so if you folks don't have any other questions, I guess I'm going to end it here. So if I don't see you, or if I don't hear from you in Physics 210R this afternoon, have a good weekend.